here's a regression problem to think about. We've got a table that shows which month a WGU student is in and how many times that student cried that month, because math is a challenge. So we see the months vary from 1 to 36, and the number of times cried during any given month from our list of 8 numbers out of those possible 36 different months. The times cried vary from 8 down to 1. Now, before you think about anything, you want to realize that one's going up while the other's going down. So your brain should be registering for you, oh, negative correlation. Now, what else that means? Negative relation, negative correlation, negative slope, something like that. Up versus down. All right, then continue on. The equation of the least squares regression line is y equals negative 0.1785x plus 5.6819. Well, that's great. We've actually been given the equation. We don't have to slam this into our calculator and do two variable statistics on it. The equation's given to us. So what kind of questions are they going to ask? Which two statements are true? Oh, we have to identify what's true and what's false. And there's a little note, round answers to tenths. Okay, we'll just make sure to do that. So we take a look. A, the regression line predicts that the student in their 26th month. B, the regression line predicts that. C, the regression line predicts that. Oh, okay. We don't know how good this regression line is, but there it is. So it does make predictions. Remember, they haven't given us any data about the R value or the R squared value. The R value would tell us the quality of the fit of this line to that data. But we haven't been told, so we can't make any deductions about the quality. We can just make numerical predictions. And that's all it is, right? I mean, to work out A, you simply need to take the number 26 and plug it into that equation, right? That's calculator work, you know, tickety, 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 and you would come out with, I've got the reference here, 1.04, blah, blah, blah. And you would round that to 1.0. Same for the 4th month. 4 becomes X because that's the month that the student is in. Tickety, 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 and out comes 4.996. Here, I'll write them all that I've got. 6979. All right, well, you know, that rounds to 5.0, so that makes sense also. So those are true. And then for the 2nd month, plug that in. You know, this seems reasonable because, you know, the smaller the months, the higher. So 6 doesn't seem like a bad prediction. Plug it in, tickety, 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 tickety. If you make a sign error, if your finger slips and you forget the minus sign, then you'll get 6.03. And you'll think the answer is 6. But that's if your finger slips. If your finger does not slip, you'll get 5.32 and so on. And that rounds to 5.3. So this one is false. C is false. Note, I did tell you the why that distractor was chosen. 2 reasons, right? One, it seems to fit the trend, right? The smaller, the bigger. That fits the table over here. The smaller the months, the more crying, right? It's tough at the beginning, and then you get used to it, I hope. So it sort of fits with the data. And if you're not thinking, if you're trying to sort of gauge things off the chart, maybe you would believe it, you're not supposed to do that. You're supposed to type it in and get 5.32 and round to 5.3 and go, that's wrong. But that 6.0 was also chosen for a second reason. A very small typewriter error of dropping a minus sign, typing error of dropping a minus sign, would get you something that rounds to 6.0. So please, when you do your tickety-ticketies, don't fumble the fingers and don't let the mind hiccup. Be careful and slow and deliberate. All right, so what's next? What we have to do next is continue. Sorry. My mistake. That should have been 3 statements are true. So otherwise we would stop. We would have confidence. We would maybe double check our arithmetic and then move on to the next item. So now it's a matter of eliminating one of the last 2. Okay? Predictions made by the regression line are accurate because there is a strong negative linear relationship between the 2 variables. Well, there is a negative relationship between the 2 variables. That's absolutely true. Right? There's a relationship and it's linear. I mean, it's negative, but we don't really know whether it's strong, and worse yet, we don't even know if it's linear. So this one's very questionable. I mean, remember, we did least squares regression line computations just because that's all you've talked about. That's all you've seen computed. There are all kinds of other regression curves that can be done. I mean, we've all seen rocks flying in the air. They describe an upside down parabola. Why would you do a linear regression on data if maybe you were using a sensor to check the arc of something moving through the sky under gravity? You know, it's at long range, so you're going to get some mess and there's some messiness in your data collection. So there's a little bit of shakiness to the data, but you want to find out what would the clean parabola prediction be. You'd better do a parabolic regression line. You can do that. Technology can do that, but we only discuss linear. So we can't say it's strong because we don't have the R value. And we can't even say that the relationship is linear because we haven't looked at it. That's really the only way to figure out whether the relationship is linear, to draw the scatter plot. Now, you don't really need to go out and draw the whole scatter plot carefully. You can just kind of look at it and take a look at this. In 2 months, it drops 2. 3 more months, it drops 2. 3 more months, it only drops 1. 3 more months, it only drops 1. 6 months, it drops 1. 6 more months, it drops 0. 12 more months, it drops 0. So you see that it starts out dropping 2 and then winds up dropping 0, and the time intervals get longer. That's not a linear relationship, right? Linear relationship would be up 2, down 2 would mean up 2 more, down 2 more, up 2 more, down 2 more, or at least approximately that. So that's a very questionable one. All we have to do here is see if E is worse. We'll pick the better of D and E. There is a strong curvilinear relationship between the 2 variables. Well, we don't have evidence it's curvilinear because we haven't looked at it. And again, we don't know whether it's strong. But at least it says curvilinear. Curvilinear means it's a relationship, but not described as a line. So we really have 2 question marks. We really have no choice but to sketch out the data. And that's exactly what you do. You just try to keep it vaguely to scale. 1, 3, 6. So if that's 6, then I go out here to 12. If that's whole thing is 12, then this is 24. And if there's 12 more to 24, oh my goodness, I got to go out here to get to 36. So we're starting to, even with this, get a little feel for what's going on. 12, 6, 3, 1. And of course, our top data is 8. And we'll do the rest by halves, right? 4, 6, 2, 1, right? This is taking a little while, but it might be worth it, right? You could just say, you know what, I got 2/3 credit, I'm going to move on. Or you might really want to just spend a little bit of time on this. Those of you with excellent calculator skills can probably type things in and then just look at the data faster than we can do a manual graph. But here it is, right? Now we can do it. At 1 month, there's 8. At 3 months, there's 6. At 6 months, there's 4. At 9 months, halfway between 6 and 12, we're at 3. At 12 months, we're down to 2. At 18 months, another halfway mark, we're down to 1. And at 24 and 36, we're still at 1. To me, this looks very much like exponential decay. That's what I'd try to guess it as. This really doesn't look much like a line at all. And in fact, I just, I cooked this up for you so I could plop it in and show it to you. It really is very much exponential data. I've got a little screen snip of the graph done to perfect scale that I just wanted to toss in the corner for you. That's what the data looks like. And that's the linear that's the linear regression line, which as you see is not very close to very many dots at all. It looks like it's only moderately close 3 times really out of these 8 data points. So not a very good regression line. That's perfectly fine. We took exponentially decaying data and tried to fit a line to it. So not good things are going to happen. Well, and that's the point. By looking at it, you went, you know what? That is curvy. So curvy linear looks pretty good. Strong? Don't know. But it's certainly better than saying it's a strong line, because it isn't. It's a strong curve. All right. E is better. Not promising that it's best, but it's better. And when you're asked to do 3 true, you certainly don't want to enter C because you know that's wrong. It's a tough one, but it really gets you thinking. It really makes you think about the fact that it's not always lines. You can do, non-lines with your calculator, with Excel spreadsheets, with software online. It's very simple to get non-line fits. And a lot of things in life are exponential decay or exponential growth. A lot of things in physics are parabolas, upward and downward. So when you really apply the stats, you're going to have a much richer way to use it. For now, just think about would a curve be better, and that'll get you through what you need to do. And also know how to compute, and that's just simple algebra done very, very, very carefully. There you go. I hope this is useful.